Okay, good evening, everyone. So today is the week 5 of the live session of many body methods in quantum chemistry. And so the goal in this lecture will be, so in week 5 you have learned so far about the basis sets, and so in the week 6 you will learn about the other Slater rules. So in today's lecture, actually I'll discuss about the Koopman's theorem in detail, where I'll derive the expressions for IP, like how in Koopman's approximation it is coming out to be the negative of the orbital energy, that I'll explicitly prove. And then again I'll prove for the EA also, which will be very similar to the IP proof. Then we'll solve an assignment problem, which is kind of double ionization potential. And in the later part of this live session, I'll discuss the slides that is actually there in the online by David Sherrill, where most of the things you know, and there are many things that might be new to you. So it would be better to discuss there. And in that section, I mean, in the basis set part, I will also discuss about one problem, which is actually called Gaussian product theorem, and that I will also prove. So, so let's begin the today's lecture. So, as many of you had doubt on this Koopman's theorem, so I'll start with this. So, Koopman's theorem. So, before going into the Koopman's theorem, so what do we know about the orbital energy? But we know the Fock eigenvalue equation, which is if your Fock is F, and if you have F chi j, and it's giving you the orbital energy times the orbital back. So this is your pseudo eigenvalue equation. All right. Now, so as this is a eigenvalue equation, so there will be a numerous number of solutions. So now if you have n electron, so if you have n electron, so then you will find out the lowest n orbitals or n chi I set, and you will fill the electrons and you will get the Hartree-Fock determinant, which is the lowest in energy. But you will have actually like many numbers of solutions. For example, if this is your n level, so there are many others also, right? Because this is an eigenvalue equation and it has a many solution depending on the basis set that you are using, whatever. Now, and as your Fock is a Hermitian matrix, so that means your chi or the this basis set, that is the orbitals chi, actually they are orthonormal. So with this, from this equation 1, if you left project with let's say chi, so if you have chi j, so then you will have chi I ej chi j. Now this epsilon j is just a number, so it will come out and you will be left with chi I chi j. And this inner product or dot product is nothing but your Kronecker delta. So this is only valid when your I is equal to j. So that means if j is equal to, if j is equal to I, so chi I f chi I is equal to your EI. So your orbital energies has this form, right? So now we can further break down this matrix element. So this is nothing but the diagonal elements of your Fock matrix Fii. So we know that F1, so this is the coordinates of electron 1, which is actually your core Hamiltonian H1. This contains the electronic kinetic energy and as well as the attraction energy over the nucleuses. So this is your core Hamiltonian, one electron core Hamiltonian. Then there you have term like summation of j over is equal to 1 to n integration of chi j star 2, and then you have 1 minus p12 by 1 by r12 times chi j 2 d tau 2. So this is your Fock operator, right? Now, so you have the orbital energies chi I is equal to, sorry, epsilon I is equal to, sorry, your epsilon I is equal to chi I for chi I. Now, so this part, this chi j star 1 by r12 chi j2, that we can call as a Coulomb operator, and this chi j star 2 minus this permutation operator and by 1 by r12 and chi j2, we can call it as your exchange operator. So we can call this as j and j minus k, right? So we can write this Fock as H plus summation over B JB minus K. So there I have written over summation over J. So this is so over J, and J is a dummy indices. So you can write it with B itself. So you have this Fock operator here. Now, if you plug in this Fock operator in this matrix element, you have EI, chi I, H, chi I, plus you have summation over B J IB minus K IB, right? Which we can write it as H chi I. So now if we like write down the whole thing, which is actually your IB, then 1 by R12 IB, then your permutation operator. So this is summation over B is 1 to N, then you have IB 1 by R12 BI. So that we know, that is your Coulomb minus exchange. This is nothing but your antisymmetrized integral. So this is summation over B is equal to 1 to N IB IB, right? So this is the expression for your orbital energy. And this is the antisymmetrized two electron integral. So now what does that mean? What is the meaning of this orbital energy? That will come in will come to this in very soon. So now if you look at this actually says that when if your electron is in chi I orbital, then this element, this one electronic part or core electronic part, this actually says the kinetic energy plus the interaction or attraction energy over the nucleus. And this term, this Coulomb minus exchange, is actually basically with all the electrons, the interaction between them, the Coulomb minus exchange when the electron is sitting in the chi. So this actually says that this is the interaction. It has a kinetic energy. It has a attraction with the nucleus and the interaction with the all other electrons. So that's what it should be, right? Now, if you take the summation, so now you have EI, right? So now if you take the summation over all the orbital energies, what you will get? You have chi. Now you will get summation over chi h chi, because what was your EI? EI was actually your chi h chi plus summation over b ib ib. Now if you take the summation over all I, so you will get I to n plus summation over b and summation over I. Now you have IV times IV, right? So this is the summation of total orbital energy. So this expression is the total sum of orbital energies. Now what is the Hartree-Fock energy? E Hartree-Fock, that you all know, that is actually I is equal to 1 to n chi I h chi I plus 1 by 2 summation over I and summation over B IB IB. So certainly your E Hartree-Fock is not equal to the summation of orbital energy. And why is that so? I think you all know this, because if you take a look at this term, this actually double counts the interaction energy. So this I actually goes from 1 to n, and this B can actually also go from 1 to n. Okay, so for any I, you are actually taking the interaction with all other B electrons. Now for the B electron, so the electron that is sitting in the B, you are taking all the summation. So you are actually counting the interaction twice. So which should not be the case, right? So but that is actually taken care in this with this half. So it ensures that in Hartree-Fock energy you don't count the interaction energy twice. So that's why your Hartree-Fock energy is not the summation of orbital energies. Now let's go to the Koopman's theorem. Now let's say we are denoting something. So if you have n number of electrons, so let's say this is your n orbitals, and there are other virtual orbitals. We call this as virtual space, and we call this as occupied space. Okay, so there are n orbital in the occupied space because you have n number of electrons. So we are going to designate the occupied orbitals as A, B, C. But in recent papers, or generally actually for the virtual orbitals, it is denoted with ABC. And for the occupied, it is denoted with I, J, K, and all. But to give the same notation as in Szabo and Oslund, I am just saying this occupied as ABC, and for the virtual, we'll talk about I or RST and all. So we'll denote virtual with RST and for occupied with ABC, this kind of notation. So now tell me, for a occupied orbital energy EA, so A for the occupied energy, how we are going to write the E, so epsilon A. So now you look at this expression EI, so you just have to do the replace with chi A H chi A plus summation over B, and you have AB AB, right? Where B goes from 1 to n. So B goes from 1 to n. Right. Now can you simplify this more? So here the only the summation is over B. So B can be 1, 2, 3, 4. So there will be certain terms where B will be A, like B will be equal to A, because your A orbital is a part of your occupied space, right? So when B goes from 1 to n, so at a certain index, B is equal to A. So when B is equal to A, so AB, you can write it in any way. So this is actually basically AA, right? So what is this term? This is actually 0, right? Because this is AA minus AA. And remember, this is called the self interaction. So what does that mean? Your electron 1 is in a spin orbital and electron 2 is in a spin orbital, right? So that means, first of all, this is not possible, and this is called the self interaction. And in Hartree-Fock, these self interaction terms exactly cancels each other. But in DFT, this is a major problem, that the self interaction term actually doesn't cancel, because you don't know the exchange correlation and all. So I'll not go into this, but this self interaction term where your A is equal to B, this actually gets cancelled. That is equal to 0. So we can write, when your B is equal to A, when your AB is 0. So we can write this chi A H chi A plus B goes from 1 to, sorry, B goes from 1 to n, and AB, and there is one condition, is that your B is not equal to A. Okay, so this is the, so you are actually cancelling one term from here. So this is the expression of the orbital energy, which is a part of your occupied space. Now, so this is for the occupied space. Now let's go to the virtual space. Virtual space. So we told that we'll denote it with RST. So ER. So what will be the orbital energy? As simple as that. This is your chi R H chi R plus summation goes from B to 1, B is equal to 1 to N. Then you have RB, RB. Now tell me whether you can simplify the things just like the above. If you notice, this R actually belongs to your virtual space, but the summation that the B goes from 1 to N, this is in the occupied space only. So you have n number of orbitals, so your sum goes from 1 to n. So there will never come the R orbital. So here all the terms will survive. right? So there will be no term where B is equal to R. Now, what does that mean? So this ER actually looks like, let's say this is your chi R, and there are n number of spin orbitals, chi 1, chi 2, up to chi n. So this expression, look at this very carefully. It actually tells you if you have an electron in this chi R orbital, so this represent the kinetic energy and the interaction with the nucleus. This matrix element represents those two terms. And what about these terms? These actually represent the interaction with the electron sitting in R orbital with all the other orbitals present in your Hartree-Fock determinant. So it's kind of the energy required to put the electron in chi R. So you have a electron cloud there, right? N number of electrons, you have electron density. When you are putting one electron in the chi R orbital, so that tells about the interaction with all the electrons present there. So I'll come back to this again, but this actually tells you that, right? So is it clear? Okay. So now if it is clear, and this is very important. Now let's go back to, so I'll come to this slide later. Now let's prove the Koopman's theorem. So now let's try to calculate the IP from a very crude approximation, which is called the Koopman's approximation. So what is IP, or ionization potential? You know from your 10th class that this is the energy required to knock out one electron and it will go to the continuum. So you will have a n-1 state, and you are ejecting one electron from the n electron space. So the energy required for that. So what is the energy difference? The delta E, which is your ionization potential, will be actually given by En-1 En, right? Where n is the number of electrons present in the system initially. So how we are going to calculate this? So let's say you had n number of electrons and you did the Hartree-Fock. So you got actually again the same thing. You got the n number of orbitals, and there are virtuous orbital. It's right. So okay. So now if you eject this electron, so you will be left with n-1 number of orbitals, right? Now this space will actually move here. So now this is your virtual orbital. You have ejected out the electron, so now you have only n-1 electron. Now if you see, when you have n-1 number of electrons, so that means your electron density has completely changed. So now the Hartree-Fock orbital that you got from the n electronic solution or n electronic self-consistent field method, so that is no longer going to be the same orbitals from the n-1 electronic solution, because your density will have n-1 number of electrons. But here we assume that even if I remove one electron from the n electron space, we'll be left with the same number of or the same orbitals. So that is the actually approximation we are making here, that even if we do the so that means we are not going to perform the Hartree-Fock for the n minus 1 electron. So we will do the Hartree-Fock for the n electron, and whatever the orbitals we have got, we'll keep those orbital as it is, and from that we are going to calculate the ionization potential. So that is the approximation. But in real case, you have to again do the Hartree-Fock for the n minus 1 electron, and then you take the difference. That is actually called the delta SCF, that I will come in the slide that I have kept there. So that is a delta SCF, and obviously your n electronic, so when you do the Hartree-Fock, that is the upper bound. So below you have an exact solution, and same goes for the n minus 1 electronic system. When you do the Hartree-Fock, then there is the exact energy below that. So that is actually the experimental result. Whatever. Now, clarifying this approximation, let's calculate the ionization potential in terms of the Koopmans. So in Koopman's picture, let's say we are ejecting out electrons from the C orbital. So there was A, B, C. I told you that they are the occupied orbital. So I am removing one electron from the C orbital, and this is your Hartree-Fock energy. So what will be the difference? We need to calculate that one. So you know that your E0n, or actually this is the Hartree-Fock energy, which is basically the summation over A. So I'm not writing chi A, so just I'm writing A here. This is A H A, and there is a half, and there is 2 summation over AB. So now you have AB, AB. So this is your energy, Hartree-Fock energy for the N electronic system. And if I remove one electron from the C orbital, and you have a N minus 1 electronic system, so now your summation goes from A. Now certainly it will go from 1 to n minus 1, and your A not equal to C. Because now in this n minus 1 electron, your C orbital is empty. So your summation, so that is actually virtual space, right? So your summation will not include that term where A will be equal to C. I think this is clear. Now again you have this half A B. Now you have AB. So again, this will go from 1 to n minus 1. This will go to n minus 1. Again, this A will also be not equal to C, and your B will also be not equal to C. Now you take the difference. So now if you take the difference, look at carefully, this Hartree-Fock energy, it contains all the term. However, this En minus 1 doesn't contain the term where your A is equal to C, right? Or so it will not contain the A not equal to C. That means only those terms will be left. So you have to find out those terms which are not present in this, and obviously that will contain the orbital C, right? That is how you'll actually calculate. So your IP, so see, this is EC n minus 1 minus E0 n. So the terms that are not there in the n minus 1 energy, so they will come as a negative, right? So you have CHC, because this term doesn't have this CHC term, right? But this summation, it contained the CHC term, and that you are subtracting it. So that means this term will only be there. So you got this CHC, and now let's look at the summation, and which is actually the critical one. So you have two summation, 1 over A and 1 over B. So A goes from 1 to N and B goes from 1 to N, right? So now let me write it separately. So there will be, now let's say you are summing over A, right? And now you'll be left with, so look at this term, this term. So you are summing over A. If your B is C, so see, when your B is equal to C, now you can take summation. So all the terms, this AC, AC, so this term actually was not there in the En minus 1, so they will survive. And again, you have to take, and so like you have two summations, right? A over A and over B. So we have taken the summation over A, and what about this? I'm just separating out these two terms. So now you are taking the summation over B, so you have to put A is equal to C here. So CB, CB, right? So let's write this term again here. IP is actually the delta E difference we have taken, which came out to be CHC minus half AAC over summation over AAC AC. And now if you look at the carefully, this summation over A is 1 to N, and this B is also 1 to N. So AC, AC, and then you have summation over B, CB, 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 right? Now this B is a dummy index, so I can always write AC, AC. I can write it in terms of A. I can replace this B with A. So you will have CA, CA, right? Now take these two terms here. So you take common minus half. So now you take the summation here. What you are left with? You are left with AC plus CA, CA, right? Now, if you look at these two terms, they are actually same. So AC, AC, you can write it as, now if you use the um, symmetry here, you can see that if you switch these two and these two, they are basically the same, right? So you have CA, CA here. So they are same, right? Or maybe I can show you. This is your AC, AC minus AC, CA, right? Now, in the Dirac notation, this is your 1, 2, 1, 2. You can switch it. So you can write it as CA, CA, and you can also do the same here, CA, AC. And what is this? This CA, CA minus. So here you have 1 by R12 that I haven't written here. So this is actually nothing but your CA, CA, right? So I've just used the symmetry of these anti-symmetrized two electron integrals. So now you can write this as CHC minus half summation over A. Now you have 2 AC, AC. And which is CHC. And now this will cancel out each other. Now we have summation over A, AC, AC. Take the negative common. We have CHC plus summation over A. So actually you can write ACAC or CACA, whatever you want, but to maintain the same notation, we are going to write CACA. They are actually same. CACA. So now you have CACA. And what is this term in the parenthesis or in the third bracket here? This is nothing but your orbital energy of the Cth orbital. So hence it's proved. So Koopman's theorem said that your IP is basically the negative of your orbital energy, right? So that we have proved there. Now go back and see that the EA is ER here. So this is the chi R H chi R summation over RB, right? And in the similar fashion, you can prove the EA also. What is EA? Definition of electron affinity is that the energy of the neutral or your Hartree-Fock. So again, here we are doing the same approximation. So you have an n electronic system, and you are assuming that if you add one electron, though its electron density is changing, so its Hartree-Fock you have to do differently. You will get different set of orbitals, but we are not going to do it. We are assuming that okay, we are done with the n electronic Hartree-Fock solution. So even if we add one electron only, so my reference state or the orbitals will stay the same. So now your one of the virtual orbital will actually be your occupied orbital, right? So in that case, your this will be En plus 1, right? And let's say you are adding the electron in R orbital, right? So now see, this EC actually tells you the energy you require to put one electron in the C orbital. So now let's say now you have a n minus 1 electron, right? So if you have a n minus 1 electron, so now your C orbital is in the virtual space. So we have derived this virtual space orbital here, right? Er is equal to, then we looked at that this is the interaction energy that is there. The electron is there in the earth orbital, and this is the interaction with the overall electron density. And the same thing we are gaining from here also in IP case. So now you have ejected out, like you have taken out one electron from the Cth orbital. So now your EC is waving like a virtual orbital. So, and which should be the case, right? So you are adding one electron. So it actually represents the amount of energy required to kick out one electron from the Cth orbital, right? The same expression with the ER. Now, what will be the for EA case? So if you do the same for this E0n and ERn plus 1, you can see that, let's write for the E0n, just for the completeness, I'll do it. I is equal to 1 to n. You have chi or AHA plus half summation over AB, right? And now here this is for your E0n. Then you have a negative. Now let's write down the Hartree-Fock energy for this ER, where your number of electrons is n plus 1. So now your A goes from AHA. This will go from 1 to n plus 1 actually. So you have A is equal to R term here. And then you have sum over AB, AB, AB. So now again you have A is equal to R and B is equal to R, and it goes from 1 to n plus 1. So now if you look at, so here all the terms will cancel out, but the terms with chi r, they will survive, right? And they will come out in the negative, because this is a definition of your electron affinity, right? So electron affinity is basically if you have a n state and you have a n plus 1 state, the energy difference, this is your EA, right? So you will be again left with, so this is actually the same R, because when A is equal to R, that term will only survive and other terms will get cancel out each other because your orbitals are the same. That is the approximation you made. So now you have similarly the summation over, I'll write it as RB plus, I'm writing it here in the single line, you have BR, or yes, BR. So I have replaced the dummy indices A with B in the similar fashion that I've done before. So if you do the same, now you will get RHR plus summation over B RB, and this is nothing but the negative of orbital energy of the chi r. So this is the Koopman's approximation towards the EA. Now we'll do a problem that is given in the Xavo, which solution I'll do it. I think that will be pretty interesting to do. So before that, let's look at this table. So what is the table is about? So before going into this table, let me discuss one thing that which is also being discussed in the lectures, but again for the uh, completeness, I'll discuss it here. Why IP is good for, like, why IP comes out to be good with the Koopman's approximation, but EA fails miserably, right? The expression goes like this. For IP, so this state, let's say your E Hartree-Fock or n number of electrons. Now you have a correlation energy. So whatever the energy you don't consider in the Hartree-Fock, and the difference between your E exact and Hartree-Fock is called the correlation energy. So this is your E exact for the n electron, right? Now for the n minus 1 electron, that is usually higher than the Hartree-Fock. So let's say it lies somewhere here. This is your E exact for, or we'll come to the exact later. So let's say now you have a E Hartree-Fock for the n minus 1, right? Now the approximation that you are making, this is your Koopman's, because if you do the Hartree-Fock, due to the relaxation, this is called the relaxation. Relaxations means that you are re-optimizing the orbitals, which you are not doing in the Koopmans, right? This is your Koopmans for the n electrons, and this difference is your relaxation energy. And as you all know, the correlation energy is, so if the number of electrons grows, your correlation energy increases. So whatever the difference here for the n electron, this is called the correlation energy, it will be lesser for the n minus 1 electron. So this is your E exact for n minus 1, and this is your correlation energy, right? Now, what is the exact IP? Exact IP is the difference between these two states, uh, these two states. So this is your IP exact, right? And this is your delta SCF that I'll come in the next table. So delta SCF means that you do a two separate SCF calculation and you take the difference. This is your IP delta SCF. And what is the Koopmans? This is your Koopmans, right? Now, this is your IP Koopmans. Now, if you look at this difference, if you look at this difference, and if you look at this difference here, so these two difference actually decide that whether you will get a closer value to the exact or not. So as your correlation energy and the relaxation energy sum is kind of same with this correlation energy, and this is your relaxation energy and this is your correlation energy, so they goes in a different direction. That give you, so that's kind of a luck or error cancellation, I would say. That's why you get the IP Koopmans very well, right? Now, in case of where your relaxation energies will be higher, like this gap will be much. So that is there in the table. So if you take electron from the valence, so then you are not disturbing the system too much. So your relaxation would be less, and in that case you are safe. You will get good result with Koopman. But if you are taking out electrons from the core, let's say you have a water molecule and you are taking electron from the 1s of oxygen. So now you are disturbing the system too much. So in that case, your relaxation will be much higher. So in that case, your Koopmans will be worse than the it was for the valence. However, for the EA, what will happen is that, so now let's say if this is the level for your E Hartree Fock for n number of electrons. Now you have a correlation energy here. This is E exact for n electron, right? This is your correlation energy, the difference. Now, so we are assuming that the energy of the anion is lower than the ground state. So in that case, you actually have a positive electron affinity. So now, if this is the state of your Koopmans, this is your Koopman state for the n plus 1 electron. Now, if you do the um, Hartree Fock separately, you will get lower energy. That's for sure. So this is your Hartree Fock for n plus 1, and this is your relaxation energy, right? Relaxation energy. And this difference is basically the correlation energy for the n electron. Now I have a n plus 1 electron, so your correlation energy is higher than this gap. So let's say it lies somewhere here. So now this is your correlation energy, right? Which is higher than the n electron. So this is your E exact for n plus 1 electron. Now look at the difference here. So this is your EA exact, EA exact, and this is your Koopmans. right? Now, this relaxation, this difference, and whatever the difference here, and this difference, actually they goes in opposite direction, which makes it even worse. So that's why your E a Koopman is bad. But in that case, if you look at the relaxation, so that was in the opposite direction of the correlation energy for the En or ground state here. But here the relaxation in combination with the correlation energy, they goes in opposite direction. That's why you get a bad result with Ea. So in generally, no one do like what no one does Koopman's approximation to the electron affinity, but you can get a rough estimate of your ionization potential using the Koopman's theorem, right? So now look at this table. So this is the vertical IP. So what is vertical IP? Vertical IP actually is you are in the Born-Oppenheimer approximation. So when you go to the ionized state, different ionized states, so that's kind of excited state, right? So it may not happen that its equilibrium bond length lies in the same location. So what do I mean by that? So let's say this is your ground state potential, so ground state energy, and you have a like this is the n minus 1 state. Okay, this is just a rough sketch. So you are starting from here, right? And in the same bond distance, so this is your R. This is called the vertical vertical ionization potential. And what about the adiabatic potential energy? Adiabatic ionization potential, you take the lowest point here and you take the lowest point here, and this difference is called the adiabatic. But here the reported value is in the uh, vertical energy. Okay, so this first value, so from the value you can see this is in the Hertz, right? So which is a very big unit of energy. So these are very high number, 20 Hertz. Okay, so this is your core ionization. Okay, and this your 1b1 and 3-1, this is your valence valence ionization. Now if you look at the number, let's look at this in dz value with Koopmans. You look at the number is 0.494 and the experiment is 0.463, so which is you can say around 0.05 hertz different, and this is the delta SCF. So in delta SCF surely the energy will be lowered and you will get a lower value, and that is for sure here. So that is 0.401, right? So which is a, I will say, good 0.05 times 27.2114 electron volt. So which will be not that big. Now look at this core ionization. Look at this number, 20.547. And your actual value that you expect, that should come out to be 19.83. So the difference is, let's say, 0. So here it was 0.05, right? But here it is 0.78 something in Hertz, and that was, so now look at the difference. So for core, if as your relaxation is too much, so in that case your Koopmans will perform very worse. However, look at the delta SCF here, 19.854 and this is 19.83, right? And so the difference is less. So your delta SCF actually is going to give you good result, right? And now if you look at the basis set, so now you are going from DZ, TZ, QZ. Okay, now in the slides I'll tell you what does the P means, what does the C means, and so actually this P is polarization, this C for core, this V for valence, D for double, like D zeta, Q zeta, triple zeta basis set, right? So now if you look at this number, um, like from here to here, the value actually decreases. This is not going to the case for like every time, but it generally happens if you increase the basis set, your value goes down generally. Okay, so this was the example like why you get good value for the valence for the coupons and not for core. Now let's solve a problem. The question is, so that the energy required to remove an electron from chi c, that is Cth orbital, and one from chi d. So you are actually taking out two electrons from C and D. So it's a double ionization potential. If you do that to produce n minus 2 electron single determinant I n minus 2 CD. So this actually says that you are still in the Hartree-Fock picture of the n electron. So you are not reoptimizing the orbitals. You are just taking out two electrons from C and D. So now you are actually asked to calculate the energy difference, right? So now what you can expect. So when I took out one electron from the Cth orbital, it was coming out to be the negative of your orbital energy, that is epsilon c. So here I am ejecting out two electrons from C and D. So you might expect that okay, my number will come out to be epsilon c minus epsilon d, or minus epsilon c plus epsilon d, because I am taking out two electrons. But there is one additional term that will come out to be here. So now let's do this. This is very interesting, and I'll suggest you stop the video and you try to do it for yourself, and then you look at the solution. So you have to calculate the delta E, okay, which is E n minus 2 CD E n 0. Now let's write down the term. Now you have summation over A H A. Certainly your A is not equal to C, A is not equal to D, right? And you have half summation over AB, AB, AB. Here again, A is not equal to C and D, and B is not equal to C and D, because your summation actually goes from A to n minus 2 here, and you are not going to do the summation when your A is C and D, or B is equal to C and D. That's what it means. And the Hartree-Fock energy, EHA minus half of summation over AB, AB. So now you might be tempted to write in the similar fashion that we have written there. And let's do this. First two terms, or the core electronic term, the H term, are very simple, because in the Hartree-Fock, you had all the summations. Now you don't have the C and D orbital. So the simple term is CHC and DHC, because these two terms are not there here, right? Now what about the summation? So let's write it very carefully. Now let's write half summation over, you are taking the summation over A. So your B cannot be C and cannot be D, right? So you will have A, C, A, C, right? This is one term. And again, in the similar fashion that we have done there, we will have this term also, right? We can write, actually that will come out CA, CA if you take the, like if you change the dummy indices B. So you will again have AC, AC, right? So I'm just removing that half from here. So you actually have this term. Okay. And in the similar fashion, if you do the summation over B, summation over V, so your A is actually CB, CB. Now again there was half and you had another term BC, BC. So they are same. So you'll have 2 here and this half will cancel out. So I'm just going to write CB, CB, right? Sorry, this is AC, AC, and there was this term will be DB, DB. Okay, but if you look at very carefully, we are actually double counting one term. So look at this term here in the Hartree-Fock energy. Here your A and B goes from 1 to N and B goes from 1 to N. So actually you have CD plus CD, and because you are double counting these two terms, this half factor came. So in my Hartree-Fock energy, actually this CD term was only once, right? Now if you look at carefully here, this sum and this sum, when you actually do this, all those stuff that I have done previously, you can see very clearly that this A can go from 1 to N and this B can go from 1 to N. Okay, now this A can be D, so you will get DC term here, and here you will also get, when your B will be C, so you will get DC, DC, right? But in my Hartree-Fock it was only once. So actually here I am counting the term twice here. So actually so there was only one negative term there, but I have written it twice. So to make up this, I should add TC-DC. Take a pause and think it carefully. That in Hartree-Fock, this CD term that I have written in green color, that was there only once. Because of the half factor is there. Actually that was there twice, but because of that half factor, your CD term was there only once. But in these two summation here that I have written in terms of A and B, actually these terms we have counted here twice. So to make up that one, to keep all the terms that was not there in the Hartree-Fock, so we have to add a DC-DC here. Now this is very simple. Look at this term CHC, and this you can combine, and with this and this summation, so this is nothing but your minus epsilon C minus epsilon D. That's what we have thought, that might be this is the number, but there is an additional term DC-DC, or we can write it as CD-CD. So if you look at the Szabo and Osloon, this is the term that that is given. So the to eject out two electrons from C and D orbital, it's not just the sum of two orbital energy, that's a epsilon C and epsilon D. There is an additional term, that is the CD term there. So we have proved this one. Now let's go to the slides that is given by Professor David Cyril. Most of the things you might know, but still there are some terms or some clarity that you can get from here also. So basis sets. Generally, a basis set is a collection of vectors which spans a space in which the problem is solved. For example, if you have a two-dimensional problem, like if you have only x and y coordinate, now there, if you have a unit vector I and j, any vector a, you can write as a summation of over a I cap b j cap, where your a and b can be anything. So with these two coefficients, you actually can span the all over two-dimensional space. So here your I and j actually acts as your basis for the two-dimensional problem. So here it's saying that a basis set is a collection of vectors which spans or defines a space in which the problem is solved. For the three-dimensional case, we have three vectors I, j, k. So define a Cartesian or 3D linear vector space. In the linear algebra class, I have mentioned this. Okay. Now in quantum chemistry, the basis set usually refers to the set of non-orthogonal one particle function used to build a molecular orbital. So now if you see, when you solve the Hartree-Fock problems, the kind of basis set that you have used, they were coming from a different Hamiltonians, right? You have a water molecule, so you have the solution of oxygen Hamiltonian and hydrogen Hamiltonian, so they are not orthogonal, right? So that usually is referred as a basis set here. So sometimes theorists might also refer the n electron basis set, which is something else entirely, a set of Slater determinants. Now when we'll go to the CIS, right, or configuration interaction singles, or CISD, configuration interaction Slater singles and doubles, they are actually the whole n electronic Slater determinants. So they actually represent your basis sets there. For when you will go to the couple cluster and equation of motion couple cluster, or let's say many other stuffs are there. Okay, so and why they are the basis sets or orthogonal basis set? They actually form the orthogonal basis set, because if you look at the Fock equations there, your F chi I equal to EI chi I, right? So these are the eigenfunctions of your Fock operator. So when you form the Slater determinant, actually they are the eigenfunction of the summation of all the Fock operator, right? So if you form a singles and doubles, they are actually formed with these orbitals only. So they form a orthogonal basis set for the determinant. So they actually complete and total. They doesn't violate the quantum mechanics postulate. Now basis set in quantum chemistry, LCAO-MO, linear combination of atomic orbital and molecular orbital approximation. So MOs built from AOs. So you can form any MO like pi I as a summation of I, Ci, let's say, or we can call it as mu, pi I, C mu, chi mu. If your chi mu is the basis set, so you can take a linear combination and you can form the uh, molecular orbital. An orbital is obviously an one electron wave function. AOs represented by atom-centered Gaussian is most in most quantum chemistry programs. So in general, in all quantum chemistry programs, actually we use Gaussian. Now we'll come to that why Gaussian, why not Slater? Because if you look at the hydrogen 1s solution, that is actually your Slater type orbital, right? So why we're using Gaussian? And physicists like plane wave basis set, that is actually for the periodic basis set. And if you want to solve for lattice, which is actually periodic in sense, and in that case the plane wave basis sets are used, so which is e to the power ikr and all. So we'll not go into this, but some older programs, they actually use Slater functions. They actually describe your atomic orbitals very well, but there are some certain problems in calculating the integrals, right? So that I'll come in a minute. So what is this Slater type orbital or STOs? So that you can see here that it has two coefficient, this ABC. This actually controls the angular momentum, x to the power a, y to the power b, z to the power c. So if you have a 1s orbital, so it has no angular momentum, right? So in that case, your a is equal to 0, b is equal to 0, c is equal to 0. Now if you're dealing with the px orbital, then your a can be 1 and your b and c, they can be 0. So that is the thing. And n is nothing but the normalization constant, and zeta actually controls the width of the orbiter. So large zeta means the type function. So let's say you have a e zeta 1 r, e zeta 1 r, and you have a e zeta 2 r. And if your zeta 2 is greater than zeta 1, so how the function will look like? So if this falls like this, right? So this will be your zeta 1 because your coefficient is less. So it will go to the asymptotic limit very slowly. However, as your zeta 2 is greater than zeta 1, so in that case, it will fall even faster. So it controls um, the the asymptotic limit actually, when how fast it decays. These are each atoms like, at least for 1s, however, they lack radial nodes and are not pure spherical harmonics. Okay, now how to get the 2s and 2p by controlling the ABC that is there. And it actually gives you the correct short range and long range behavior. Because in Gaussian type orbital, it depends on the R square. All the things are same, right? So it will fall very faster than a Slater type orbital. So your AOs are actually a Slater type orbital, right? But in Gaussian type orbitals, they will fall off very fast. So that's why it is written that it doesn't give you a correct long range behavior. Okay, just give me a minute. Okay, so Gaussian type orbitals, they are this e to the power minus zeta r square. Again, here ABC controls the angular momentum, and total angular momentum is actually L is equal to ABC. So for 2s, 2p, 3d, so this the angular momentum is controlled by this ABC parameters. Okay, now these are no longer H atom like or even for 1s because this is e to the power minus zeta r square, right? And this is much easier to calculate. This is because of the Gaussian product theorem. So what happens is that, uh, so now let's say you have a this mu nu lambda sigma, this type of two electronic integrals. So this is actually a force center two electronic integrals, right? So for this mu, you have a one. So in real picture, this mu actually is defined by one letter, and this nu is by another letter, and this lambda sigma. So you need actually four letter, right? And to compute this integral using Slater type orbitals, so this is very difficult, right? But if you use a Gaussian product theorem, so in that case, what happens is that, so if you represent this mu with a one Gaussian and this nu with another Gaussian, you actually can take product of these two Gaussian, which is on two different center. If you take the product, the Gaussian product theorem, I think yes, I'll come to this. So it says that if you take a product of two Gaussian, it actually gives you back another Gaussian with the summation, so which exponents are the summation of the individual one, and it it is centered on a different center, but it still remains a Gaussian. So these four-center two electronic integrals, it's reduces to a two-center two electronic integrals, and your integrals generation is very faster. So that's why people use Gaussian as your basis. So, and this is almost universally used by the quantum chemists. So we'll come back to this. It will take some time to prove this. So it says that if your one of the Gaussian, which is e to the power minus alpha x minus a square, where this alpha is your exponent, and this is centered on A, and you have another Gaussian which is centered on B, and which has and which has a exponent beta. This actually says that if you take a product of these two, you will get a different Gaussian whose exponent is the summation of these two individual um, Gaussian, and the new center is a weighted average of these two, the alpha A plus beta B divided by alpha plus beta. So that we actually will prove, and this makes the calculations of the two electronic integral very easy. Now we have the contracted Gaussian type orbitals. So Slater type orbitals are more accurate, but it takes longer to compute integrals. So because they are difficult. Now what is the solution? You can take a linear combination of enough Gaussian type orbitals so that it looks like a Slater type orbital. So a combination of n Gaussians to mimic an STO is called a STO-NG. So that means that to mimic one Slater type orbital, you need n Gaussian, even though it is made of contracted Gaussian type orbital. So why is this called unfortunate? So when you take the summation here, like here, you are forming a contracted Gaussian type orbitals to mimic a Slater type orbital. But the basis set names like a STO-NG. So this is just a nomenclature. Okay. So what's happening here is that, so you are taking sum which is I is equal to n to n. So you are taking n summation or n Gaussian summation to form a contracted Gaussian type orbital, which are actually your Slater type orbital, right? And different Gaussians are controlled by this your zeta i's, or this is the your exponent. Okay. Now look at this plot. So this Slater is the accurate one. This is your accurate one. Now, if you take only one Gaussian, how does it look? It looks like this. See the so it in the previous slide it mentioned that the short range and long range. So if you look at this, this is the short range behavior. So this is completely off from the exact one, right? But in the middle range, so this is also fine. However, in the long range also this deviates. Now if you took two Gaussian, okay, then you see it goes closer to the actual one, and even with 3G it goes even closer, right? That's what is given in this plot. Now there are different types of basis set. There is minimal basis set. So what is minimal basis set? Minimal basis set is that you use one basis function, or a Slater type orbital or contracted Gaussian type orbital, okay, for each atomic orbital in the atom. So if you have a H2 molecule, so it has you will use one basis function for the 1s atomic orbital. Okay, so in that way you will have the minimal basis set. Now what about the double zeta basis set? Double zeta basis set says that for each AO you use two basis function. We'll come to that. Triple zeta again for triple basis function, or three basis function for each AO. And then you have quadruple zeta, 5 zeta, 6 zeta, right? Now a split valence basis. So the split valence basis is actually your 631G. So in that, what you do is that you use only one basis function for each core AO. For example, 631G for core, I think it has been taught that for core orbital, if you are using only one type of contracted Gaussian type orbital, or STO, and a larger basis or two types of function for the valence one. So that is called the split valence. For example, H atom, one s AO, you use one basis function. For carbon atom minimal basis, 1s, 2s, 2px, 2py, and 2pz, you have 5 AOs, so 5 basis functions. This is your minimal basis. Now double zeta function, what you do? You have 5 AOs, so you have 10 basis function. Now for the split valence, you have 9 basis. And why? Because for 1s you will not use a two like double zeta basis function, right? So this will give you 1 and rest of them will give you 8. That's why it is coming out to be 9 basis function. Now the counting basis function is that, then this is very important. When counting basis functions with basis set that includes contracted Gaussian type orbitals, each contracted Gaussian counts as a single basis function. So when you take 3 Gaussians and make one contracted Gaussian type orbital, that gives you only a single basis function. We do not count the primitive Gaussian type orbitals functions inside a contracted Gaussian type orbital. So here is the example, 631 G star. So I'll come to that. What is the star? Carbon has one basis function representing the 1s orbital, not 6. 6 is the your number of Gaussian function that is used to make the contracted Gaussian type orbitals. Right. Now, what is polarization functions? Polarization functions, I think you know about the hybridization, right? sp3, sp2, sp. So when you have a s orbital, it has no directionality because there is a no angular momentum, but p has some directionality. Now, if you mix with s and p, it can actually give you directionality, right? So that is what written here. As other atoms approach and atoms orbitals might want to shift to one side or the other, that is the polarization, and s orbital can polarize in one direction if it is mixed with a p orbital, sp, sp2, sp3. P orbitals can polarize if it's mixed with d orbitals, like you know about sp3d, or there was this sp2d, pd, this kind of hybridization. So it actually can give you the polarization. So in general, to polarize a basis function with angular momentum L, mix it with basis function of angular momentum L plus 1. When I'll show you the example there, you will see that whatever the valence angular momentum, you take L is plus 1 to go higher to get the polarization function. This give you polarized double zeta or double zeta plus polarization basis set. That P here, that P there, right? The CC, P, CV, those basis set, that P is basically for this polarization function. Now you have diffuse function. Diffuse function has small zeta exponent. If your zeta is for small, that means you will decay slowly, right? So this means that the electron is held far away from the nucleus because your density, electron density, will go off or decay slowly in the case where you have a larger uh, like zeta exponent. Necessary, this is very necessary for anions, Rydberg states, because the Rydberg states actually your electron density lies very far from the your molecular structure. So for the anions or Rydberg states, I will say there is something called dipole bound state. There also you need a very diffuse function to describe those states. Okay, because they lie very far from the nucleus. Necessary for accurate polarizabilities or binding energies. It's very bad to do computation on anions without using diffuse function. Your results could change completely. And this is a very important note to take from these slides. Now, this is the anatomy of basis sets. So this is your H atom STO3G, Slater type orbital 3G. So this is your H atom. Okay, and this is for the angular momentum S orbital because you have only one S, right? And this is your for the S orbital. And what does these three represent? These three represents that you have a three Gaussian type orbitals, which give you the one contracted Gaussian type orbitals. And this is the exponent, or these three are the exponents, or zeta, and this is the coefficient, or Ci. So you take this summation of Ci e to the power zeta I r square, right? So these are your coefficient, and if you take the combination, you get a contracted Gaussian type orbital. Okay, now this is for your carbon atom. So for s orbital, C, you have three Gaussian. Okay, and you have 2s and 2p. So they write in this fashion, but if you go to some other program, so there you can see that the s and p are written in differently, but these are very old basis set S3G, so they write in this sp fashion. So this which share the exponents of s and p function. So what does that mean is actually that these three are the exponents for your s orbital, and these three are the exponent for your p orbital, and these are the like the coefficient. So you have a different sets of uh, zeta, but your and they have the same coefficient. That's how you written the STO3G. And then you have the Pople basis set. He was a Nobel laureate, John Pople. And STO3G is a minimal basis set that we have already discussed. Then you have a 631G, that split valence that we have discussed. I don't know whether they have given an example. Yes, they have given the example, that 631G. How does it look like? So see, this is for s orbital. and you have 6 primitive Gaussians, right? And these are their coefficients. And you have only one type of contracted Gaussian. Now come here. What does this 3 means? This 3 means that for 2s orbital, you have 3 primitive Gaussian and one another primitive Gaussian. So two types of contracted Slater type orbitals here we are using, right? And again, this is for P and another for P. So two types of contracted Gaussian. So that's why this hyphens actually tells you there this is a split valence basis set. Now this is a 631G star. So this star represents, so for carbon, you had only 2p, right? So this actually represents, so I told you that for polarization, you go to L plus 1. So the p is actually 1, right? So you go to D orbital, L plus 1, right? So this is for, so when the polarization will be only added to the non-hydrogen atom, and this is for the 631G star, and this is 63111G, the triple zeta basis set. Okay, and this plus is for diffuse function. I'll show you uh, some example. So let's, so there is a website that is called the Basis Set Exchange. You search Basis Set Exchange and you select the carbon atom, and let's say we want to see the 631G. We have already seen what is 631G star. Okay, now you click the, so this is your 631G basis set, right? Or yes, star. That means there will be a polarization. So see, this 6 is your um, code. This is for the 1s orbital. And this was the your 31G, right? 3 and 3 primitive Gaussian and 1 primitive Gaussian for your this valence electron. Now if you see, there is a D type orbital. Okay, this is for carbon. And so that's why it is called a 631G star. Now if we see that 6311G, so here if you see that it's a triple zeta basis, right? So for the valence, see there are 3, this sp, so 311G, right? There is this one and another one. So this is for the carbon atom that I'm showing you. Now if we go to, so there is a numerous number of basis set that you can find out. Let's go to 631 plus plus G. So this plus plus G means that there will be a diffuse function, right? So 31G, so this is your 3 and this is your 1. And look at the your diffuse function. So diffuse, when you add diffuse function, they have the same angular momentum. For polarization function, they are one like L plus 1. But here you will have the same angular momentum, but the basis set, the exponents will be lesser. So see here, this is 0.168, but this is actually 0.04 because this is 10 to the power minus 1. Okay, and so one for S and one for P, right? Or actually Px, Py, and Pz. So for all the valence, you add one diffuse function. So that is the meaning of your 631 plus plus G. So plus plus is basically this is for all atoms. Okay. Now let's go to this one. What is this basis set? This basis set is your 631 plus G star star. First thing, 6. That means for core orbital, you have 6 primitive Gaussian, we are done. Then you have a split balance or double zeta basis set. That means for S and P, you are using 3, 1. 3 primitive Gaussian and 1 Gaussian. You are done. Now this plus means that you have to add diffuse function. And what is that diffuse function? This is here. So you have added one diffuse function, or for actually 2s and 2px, 2py, and 2pz. So that is there written here. And there is this star star. That means you have to add a polarization function, which is one order higher, or that is d orbital. Okay, so everything is clear, and this is, so this has some other meaning, so I'll just discuss this. So let's look at this basis set. What is this? This is 6311. So this is simple. For 1s, you will add um, 6 primitive Gaussian. Then you will add this triple zeta basis set. Then you will add a diffuse function. Up to this part is clear, right? Now, what does that mean? This means that for hydrogenic or non-hydrogenic atom, you'll add a 3D function and one F function. However, for hydrogen, you'll add 3P and 1D. As we are looking for carbon, so you'll expect that you will get a 3D function and one F function. Okay, now let's see. So 311G, this is the part. Then plus plus was there, that was for the diffuse. Yes, we got it. Now see 3D D function and one F function. I hope this is clear, and there are different basis set that you can check, and so you can change the format. You can, this is a new chem, there's a quantum chemistry software, Gaussian, Psi4, QChem, Orca, whatever you want to use. MolPro, it has TurboMol, and many other softwares are there, right? So in whichever format you can want to check, you can check. Okay, now let's go back to the slides. Yes. Now the designation of basis sets. Yes, that's we have already discussed. Now there is a Dunning correlation consistent basis set. So the Dunning pointed out that the basis sets optimized for the Hartree-Fock. So where there is no correlation, they might not be good for correlated computation. So in the lectures, coming lectures, you will see about MP2 couple cluster. They are actually correlation calculations. You take care of the electron correlation. They might not be good. So they optimize the basis set, and they have nomenclature as CCPVXZ. So this is CC means the correlation consistent, this P means the polarization, V means the valence for valence, and X means if this is 2 zeta, 3 zeta, and 4 zeta, and that is actually written here. Okay, so the Dunning basis sets are designed to converge smoothly toward the complete or infinite basis set limit. There is something called CBS or complete basis set limit. Mm, a prefix is augmentation, so there is augmented CCTV. So these are just nomenclature, right? So this augmented CCTV, XZ basis set. So for every angular momentum present in the basis set, you add uh, one set of diffuse function. Okay, so that is actually meaning. You don't have to read this one because this is not that much used. And yes, there is for code that in the table that we have shown in the Koopman's theory, that when we are discussing in that table, you saw this C, that was actually for code. Okay. So these are just nomenclature. And you can see that the convergence of vibrational frequency with respect to basis set. So if you go to d zeta, t zeta, then q zeta, 5 zeta, and 6 zeta basis set, you can see that as a 4 zeta level basis set, it is almost converging with the complete basis set limit. So it's general that if you use a larger basis set, you get a good result. But one line is written there in the slide. I think you will see very soon um, that this is not the case always. So this is the convergence of bond lengths. So this is again the case that if you go to this 2 zeta, 3 zeta, 4 zeta level, okay, this actually converges with the. So higher the basis set, you get the good numbers. Now, please look at this. The bigger the basis set, the better. Usually, need to balance with correlation method. That means if you are using a bad method and a bad basis set, you might get good result. But if you are using a bad basis set and good method, or bad method or good basis set, you may not get good result. So there are some error cancellation or luck will play. So CCPVQZ is great for CCHD parenthesis T, which is a correlation calculation, but it overkills for the Hartree-Fock. STO3G should not be used. So these are the actually from the experience I think he has written, and uh, and these are very important notes. Hard to afford more than polarized double zeta basis set except for small molecules. So if you go for higher molecules, your calculations will be very costly. In our experience, the CCPV zeta is not necessarily better than 631Z DP. However, CCPV TZ is better than 6311Z DP, and convergence or ab initio result is disappointingly slow with respect to basis set. Uh, and so there are some resources that I have as basis set exchange, that have just shown you the website. And okay, yes. So I think we're done. So what I'll do is that I will prove this Gaussian product theorem in the next class. And in the next class, I will also have some interesting assignment problems that we can solve. And if you have any doubt, you can post it in the discussion forum. Okay. Then thank you.